So we're going to be finding the area of polar curves. And here's our formula: 1/2 the integral from one angle to another angle of r squared d theta. R sometimes is written as f of theta. It just depends on what the function is called. But it will always be a function of theta because it's a function of the angle. So we're going to start with an example. R equals 3 cosine theta, and I want to find the area of that curve. You would start by graphing this. Come to find out, it's an ellipse. Okay, here's the graph of it. Now, when you're setting up this formula, whenever you're using calculus, everything has to be in radians. You can leave your calculator in degrees so that you can find angles you're looking for and so that the angles make sense, but you do have to change everything back to radians when you write out the answer. So what I start with is I press trace. Notice that 0 is over there. Well, I'm going to move my angle. There we go. And I want to go all around. It won't always be 360. Notice that half of it's 90. And if I keep going, I'll get to 180 when I get to the other side. If I keep going, it just retraces the ellipse. So, there are several ways that you can do the problem. Our formula is 1/2 the integral and then the radius squared. So the radius in this case was 3 cosine theta because that's what we graphed. And then 0 to pi would work because 180 is all the way around. Or it is okay if you wanted to do 2 times 1/2 times the integral 0 to pi over 2. Since pi over 2 was halfway around, and that would just be the area of this top part. When you're using your angles, what's going on with your angles is that you're like starting wherever the first angle is, and then you're just keep like going different angles of the graph until you get to where you started, and then you're adding on that all of that up. During today's video, I'm not going to focus on what the answer is. I'm just going to focus on how you set it up because I think that part is the most important at this point. When you put this back into the calculator to find the answer, you do need to make sure you're in degree or in radians whenever you put it in your regular screen to find the answer. Degrees are okay when you're graphing it, but when you get your answer, it does need to be in radians. So we're going to do another one, 3 plus 3 cosine theta. Let's go ahead and graph this. It is one of those hearts. It's kind of a sideways heart. It's a cardioid. And I want to find this area. So I'm going to start by pressing trace. There's 0. And I'm going to move it until I figure out what's going on with the angles. Notice how it just kind of stays there. Looks like it's 0 to 180 on the top. It keeps going. I'm sure that 360 will go all the way around. So in doing this one, it would be the integral from 0. You can go to 260 or you could go to pi. Just showing you both ways, just depending on the problem. It may be easier just to do a certain part of it. You put in the formula squared d theta. You times it by 2 if you're just going to 180 because 180 is here, and 180 would be that top part, and you times by 2 to get that whole area of the bottom part as well. Alright, here's another one, 2 cosine 4 theta. I'm going to zoom in on this one just a little bit, just so that I can see those petals more clearly. The question here is wanting us to find the area of one petal of this flower. So if I press trace, it starts here at 0. Notice that this is tracing the top of a petal. It goes to 22.5. If I continue pressing it, it changes to a different petal. And I could find the angle that it started there and the angle that it ended there. Or if I keep tracing, it's going to do this petal. I could do where it started and ended. But if I went back to 0, I could go from 0 to 22.5, and that would give me the top part of that petal, and then I could multiply by 2 to get the area of one petal. So area of one petal is going to be the integral from 0 to 22.5, which I need to think about here in just a second. It's a half, because that's part of the formula, but I am going to multiply by 2 because half in one petal is just that very top part, but I need the whole petal. And the way that this was written, I would have to have 2 weird angles, whereas here I'm just going to have one weird angle, so that's the reason I'm going to do it this way. The formula is 2 cosine of 4 theta squared, and then that'll give us the answer. Now, the 22.5, several ways you can do this one. You could think about that this is half of 45. It's 45 divided by 2. I know that 45 is pi over 4. Pi over 4 over 2 is pi over 8. If you actually needed to change this one, instead of doing it that way, you could multiply by pi, divide by 180, and you would get pi over 8 there. It would be 0.125, which you would change to a fraction and put in the pi. That one was kind of strange because of where the angle started and where the angle ended, and that if you trace it, like after the red, it went down here and then went around. So you could have used 22.5 there, but then you'd have to figure out this other, I think it was 62.5 maybe, or whatever that other place was, and that would be 2 weird angles that you would have to find. Whereas the way I did it, the 0 was obvious that it started at 0. So here's another one we're going to try. 2 plus 4 cosine theta. I'm not sure the exact pronunciation of this one, but limacon maybe is the word you have seen. It's one of those that kind of looks like a cardboard, but it has an inner loop. And what I want to find here is the area of the inner loop of this figure. It could be that we want to find the outer loop, but I want to find the inner loop. I'm going to zoom in on it just a little bit so I can see that inner loop a little bit better. Alright, press trace. I'm sure that it starts way over here where that starts, so I'm just going to continue pressing it until it comes down to be where the inner loop would start. Looks like inner loop's going to start at 120. Goes all the way around until 240. So the inner loop that I'm looking for is 120 to 240. Just going to write that down. I'll come back and figure out how to change that. And since I'm only finding the inner loop, then I'm going to do the integral, and I don't have to multiply by 2 because these two angles give me the whole thing. 1/2 on the outside, the formula on the inside, square it. Alright, I need to change 120 and 240. 120 is 2/60s, 240 is 4/60s. Well, 2/60s are 2 pi over 3, so that will go on the bottom. 4/60s is 4 pi over 3, and that will go on top. So there's one where the angles weren't quite so obvious. If it were wanting outside that loop, then we would have to do some kind of subtraction. We're going to talk about what would happen in some problems that are not just one thing. All of these so far have just been one thing, but we do want to find areas like between two curves and doing some different things, and so we will look at that next. So now we're going to work with two curves and figure out what's going on, like if you wanted to find certain regions. So we have 2 and 4 cosine theta. So let's go ahead and graph that. The problem would give you an idea of how to find whatever it is asking you for. One thing it might say is find the area outside r equal 2 but inside 4 cosine theta. That would be one way that they would say that problem. If I press trace, you'll realize that the blue is 2 and the red is 4 cosine theta, and I'll write that down in just a second, but if I want the area outside the blue and inside the red, it looks like I'm going to be finding this area right in here. So since I'm finding this area here, what I'm going to want to do is I'm going to find the area of the red, like the top part of the red, and then I'm going to find that little bitty area right there of the blue, and I want to subtract the red and the blue. Now the reason I'm only talking about that top part of it is sometimes those angles just get strange, and I think it would just be easier for us to find what we're needing for. So we're going to start off with the red, so I'm going to move my cursor back to the red, starting at 0, and let's just move it. The intersection of the two curves are 60. So it looks like on the red I'm going to figure out what the area is from 0 to 60. And then if I move it to the other one, the r equals 2 one, and start it back at 0, like I want to go from 0 to 60 again, probably, because that's where the intersection is, and I want to subtract off that. So 0 to pi over 3 would be that part, and 0 to pi over 3 of the other one would be that part. And what it would be finding is this area, and it's hard to draw on this little bitty part of it, but it's finding that little area right there. So basically it's kind of like we did with area before, how we subtract something. So it's 0 to pi over 3, because pi over 3 is where it intersects, that's 60. So this is going to be pi over 3 here. 1/2, because that's the formula, of the one that's on the outside, which we found out was 4 cosine theta. And then we want to subtract off the circle, which comes out to be 2. And because we have the 1/2 on the outside, then we're doing one of them, squaring them, and then subtracting the other, then squaring them. Then we're multiplying by 1/2. So we've done the formula twice. This is the same as saying 1/2 the integral of one of them minus 1/2 the integral of the other. And you can put them together as long as the two angles are the same. It won't always be, but it was here. So here's the next two that I want to find the intersection of, or the area of, and it would say to find the intersection of the circle and the flower, or something like that. And so I'll show you when we graph it. The circle does intersect the flower, and there's two little parts that we're looking for. I'm going to press zoom in just because that's really small. It's hard for me to tell what's going on here. So there's the circle and the flower. And I want to find the intersection, so I'm trying to find that little part right there that's in the circle and the flower, and then that little part right there. Alright, so what we're going to have to do is we're going to have to find where everything intersects. Okay? So if I start like with the petal one, let me write down what the equations were. It's r equals sine of 2 theta and r equals cosine of theta. So if I press trace and try to figure out my angles, if I start with the petal one, then 0 would start here in the center, and then it'll intersect the circle right there at pi over 3. So if I go from 0 to pi over 3, and then of something, which I'm still not too sure about yet, what that's going to give me, like if this is the whole petal, it's going to give me this part of the petal to there. Because that's where it intersects the circle. The circle would be coming around here. And so that's where it intersects the circle, and so it would find that part of it. Well, if I multiply that by 2, that would give me that whole petal right there. So I'm going to put a half and then a 2. And I wrote that wrong, and I'm sorry, but it was pi over 6. And although I didn't show you the trace, I think you can trace that, and you can see that that angle would be pi over 6. Now, to figure out the top part of it, like to figure out from pi over 6 to that, see that part of it is the circle. That blue that I just traced is part of the circle. So what the blue would be finding would be this area here. If I figure out the intersection between there, which we know is pi over 3, to there, or pi over 6. I keep saying pi over 3, I'm sorry. So if you trace that to here, that angle would be pi over 2. So what I want to do is I want to add what's going on from pi over 6 to pi over 2. And again, that's just finding one petal, so multiply by 2, and then that will help me find both pieces. Okay, so the red is this bottom part of the petal, the yellow is the top part of the petal, and then by timesing by 2, I'm finding 2 parts of the petal since there's 2 parts that are shaded. Now, the 0 to pi over 6 one was the petal one, so this should be sine of 2 theta squared. The pi over 6 to pi over 2 was the cosine one, so that one should be cosine of theta squared. And what you do is you add those together. I'm going to go back for just a second and show you on the graph, as far as the tracing, how that works. Okay, so see, I'm on the petal right now because I'm on the blue one, and if I move it over, you see how it intersects at 30, so that's why it was pi over 6 that I was working with. And now if I change to the red, because see, I want to stop it at the red, I don't want to go all the way around the petal, I just want that red part of it. So if you move up, that takes you to the red, and now move it over, and notice that that stops at 90. So that's where I'm getting those numbers. It's going from 0 to pi over 6, and then pi over 6 to pi over 2. Alright, so here's 2 more. And I want to find the area inside the one with sine, but outside the one that just has a 1, and that's a circle. There's that graph. So inside that blue one, outside the red one, so it's just talking about this very top part, like the hat of that kind of thing. This one's a little easier than the last one. Press trace. Notice that it starts really nicely over here. If I find out that all the way over there, then that would be good, and there's not like an intersection like there was on the last one that I have to really worry about. So it looks like they intersect at 180, so if I'm just finding that part, it's going to be from 0 to 180 of the blue, 0 to 180 of the red, and then I'm going to subtract. So the blue was 1 plus sine of theta, and the red was 1, so it would be 1/2 0 to pi of 1 plus sine of theta squared minus 1 squared. That one was a little easier because all you had to do was just the blue minus the red, and the intersections were nice, and you just had to do that whole entire thing. Alright, I have one last one, 9 cosine theta, 9 sine theta. And the area it wants me to find is inside both of these circles. Let's go ahead and graph it, see what it looks like. It's wanting me to find this area right here. Okay. Let's press trace. I think I want to start on the red, so let's just go up and see what happens. Since that starts there, and since that area right there is what I'm looking for, then that's really nice. So we're going to start there at 0 on the red, and we're going to move it until I get to 45. So 0 on the red to the 45. That would give me what I need on the red, but then I would just have to subtract something else off. Alright, so if I press up and get to the other one, the blue one, and then start from there, the blue one goes from 45 to 90, so it looks like what I can do is I can go from 0 to 45 on the red, and that will give me like this little half part of the circle, and then 45 to 90 on the blue And that would give me that top half, and I would add them together. This is kind of like the example that we had on number 2. So it sounds like we're going to go 0 to pi over 4. And that would be the red one. The red one ended up being 9 sine of theta. 1/2, because that's part of the problem. 1/2 r squared. And then I want to do pi over 4 to pi over 2 of 9 cosine theta, because that's the blue one. So when I go 0 to pi over 4, I'm finding that part of the petal, or the area, and then from pi over 4 to 90 is that part, so that's why I'm adding it together. And like I said, that's kind of like example number 2, how you had to find like one part of it and another. Now example 2, we multiplied by 2, and that's because there were 2 petals. On this one there was just that one little bitty intersection, so we don't have to multiply that by 2. We'll do some more of this in class, but I hope that's given you a good overview of the kinds of areas that you'll find with polar.